Talking about current, it's a flow rate, a rate of flow of electrons. You can see I've got a source here that's moving electrons around this circuit. How fast are they coming? Well, we can measure. If we sit here and count them as they cross this line, that'll tell us how fast they're coming. If we count them and time them, we know their rate of flow. In the field of electricity, if I can get 6.25 billion electrons to go past this point in 1 second, that rate of flow is what we call 1 amp. So 1 amp is not a quantity of electrons. It's a quantity of electrons per second. It's a big quantity, 6.25 billion, which they call a coulomb. A coulomb is just like you call 12 eggs a dozen. You call 6.25 billion electrons a coulomb. So if I can get this to move around here at 1 coulomb per second, that's 1 amp. Voltage is the difference in electric charge between 2 points. We said the difference in electric charge is because there's more electrons that are negative in charge in one place than there are in another place. And so I've got electrons down here more than I have up here, and that's why this part is negative. And I don't know exactly, although I could find out, or so could you, how many electrons it actually takes, how many more electrons I have to have down here to make this difference 1 volt of force. But whatever that is, whenever you get that much difference, that tension builds up that it'll move 6.25 billion electrons through 1 resistance of ohm in 1 second. So there's 1 amp. It takes 1 volt, if you're faced with 1 ohm resistance, to move 1 amp. And that's kind of what, this is the schematic. If I have 1 volt forcing electrons and I have 1 ohm opposing the flow of electrons, the balance of those 2 forces results in 1 amp. Magnets, here I've got a difference in polarity and there's a force here, but if I increase the difference, now you can just imagine that there's more force. So that's the same thing as happened here. I add electrons, this force gets stronger. I add magnets, the force gets stronger. And with that stronger force, there's a greater tendency to cause motion. In this case, metal, and in this case, electrons. Resistance is the opposition to the flow of current, and it's completely caused by friction. Electrons are trying to move through a conductor, a wire, or a trace on a circuit board, trying to move through it, but it's rubbing against other electrons and the rest of the atoms. It's friction, and that friction causes heat. Just like when you're rubbing your hands together, it causes heat. And so down here, I've got voltage that's trying to move electrons through a conductor, and I've got the resistance that's trying to push it back or resist it. And we can see that if I were to back off on this resistance, then more electrons would flow, or they would flow faster, however you want to look at it. And we could also see that if you increase the force behind the push, then you're going to have increased flow. Let's say that this is a box, and in that box is 6.25 billion electrons, and I'm trying to move them because I'm a battery. I'm trying to move those, but there's friction that kind of fights against me. And I think you could see that the speed that I'm able to move this, the flow rate, is based on how much push I have and how much opposition I'm getting to my push due to friction. And that if I were to reduce the friction by spraying lemon pledge all over the floor, you could see that I would be able to increase my rate of movement. And you can also see if my buddy came and he was the same as me and we doubled the exertion here, the force, again, that would cause an increase in the speed. So this relationship that we're talking about here of voltage pushing electrons and resistance opposing them, and that flow of electrons is current, these are your real basics of electrical circuits. It's important that you have that understanding of that relationship. Energy. Energy is the ability to do work. Energy is power times time, and we measure it in kilowatt hours. Kilowatts times hours. And this is a typical meter that you would be familiar with that measures energy. Energy is different from power. Power is how much energy is being used in a given length of time. So how much work are you doing? How fast, how quickly are you doing work? That's what power is, how quickly you're doing work. Energy is the ability to do work, and power is how quickly you're doing that work. Electrical power and a lot of other kinds of power expressed in watts and kilowatts. Here I've got a box and I'm moving this box. My work is moving a mass times a distance. So the work that I'm doing is moving this box. It's not going very fast, but if I were to make it go faster, to get this same amount of work done, moving it from the front to the back, get that done faster, I would have to have more power. Probably that motor is measured in horsepower. Some electric motors are measured in horsepower. It's made of volts and amps. Power is equal to voltage times current, or watts is equal to volts times amps. We talked about continuity, and we'll talk just a little bit more about that. You can see up here in this example, I've got L1 and L2. This stands for line 1 and line 2. So that would typically mean AC current, probably 120 volts. This is one side, and there's nothing that's drawn connecting this, but we're assuming that there's an AC power supply that's pushing current through this way and then returning this way, and I've got my loop. So you'll see drawings that'll be indicated like this, L1 and L2. Know that this is like the prongs of a plug-in on your lamp. This plugs into one slot and this plugs into the other. There's something behind it. L1 is trying to push electrons, but it can't because I've got an open circuit. This has broken the continuity. Consequently, none of them are going through the load, so no work is being done by the load. Over here, the switch is closed, so the electrons can move through that, and that would make that work. Same thing that's going on here. It's much like a drawbridge. Whenever you open that up, the traffic has to stop. You don't get any flow until that's closed again. Speaking of bridges, oh man. This shows a little bit, again, that relationship with force over here. This force is being created from this head of water. The flow that results, and remember that the current is a result of the voltage and the resistance. And this is what you're seeing here. An increase of resistance starts to decrease the flow. All right, so all this stuff we've been talking about, this relationship between voltage, resistance, and current is Ohm's law. Ohm's law expresses that in an equation. Now, I tell you that when you're doing technical work, you don't necessarily have to come up with very precise numbers. Most of the time, you just need to be in a ballpark. If I'm looking at a circuit and it says on the drawing that it's supposed to be 9 volts, but when I put a meter on it, it says that it's 8.85, that's probably not what's causing the thing not to work right. Usually you're going to see like the voltage is going to say nothing, or 2 volts when it's supposed to be 9. Now you got a problem. Again, a lot of times you just need to be in a ballpark with stuff. So don't ever approach a problem too much in detail. Don't get in that thing about you can't see the forest for the trees. Before you start digging into a lot of prints and really doing the heavy head work, and step back and make sure nobody kicked off a piece of conduit or a fork truck didn't knock something off, a limit switch or something off that's causing something not to work. But sometimes you do need to calculate numbers, and that's what Ohm's law is good for. What's more important is what I've been trying to get across to you, that current is the result of the interaction between voltage and resistance. Okay, so I've got a 12-volt source and I have a 3 ohm resistance. This thing's pushing as hard as it can. This 12-volt battery is pushing as hard as it can to move as many electrons as it can against 3 ohms, but it's only going to get so far. It's locked in stone through physics that it's only going to get 4 amps, no more, no less. It's going to get exactly 4 amps. If you have exactly 12 volts at exactly 3 ohms, 4 amps is the exact result that'll happen. This little animation here kind of shows what happens when you change the voltage of your power supply and how much current flows, and when you change the resistance. So again, you won't be able to see this if you just look at if you just view these slides in Google, but if you download them and play them in PowerPoint, then you'll see these things that we're seeing in class. Let's solve a problem. 48 volts. It's trying to push as much as it can through that 3 ohm resistor. But given that that's exactly 48, and given that that's exactly 3 ohms, an exact amount of current will result. How much?
16 amps.
16 amps.
16 amps. All right. So looking over here, the way this little wheel works, I don't know what I is, so I'm going to go over here to I and see how to get I. Well, I can get I by taking the square root of power over R, but I have R, but I don't have the power. That's not going to be good. I can take the power divided by V, but again, I have V, but I don't have power. Or I can take the voltage and divide it by the resistance. Those two variables I do have. So I will use that one, and I will take 48 divided by 3 ohms, and I'll get 16 amps. That's how Ohm's law works. You should know intuitively that relationship between voltage, resistance, and current. This is how George Ohm, decided to put it down in mathematics to get precise numbers. What about the power? The power, I don't know, I have to go over here and look. So power, I can get any of these 3 ways because I have all of these variables. I have V times I, so I can take my I times V. I also have R times I squared, so I can take 3 times 16 times 16. I can take V squared divided by R, so I can take 48 times 48 divided by 3, and all of those will give me the exact same answer. If any of you have calculators on hand, you probably should have come up with that by now.
768 watts.
Very good. 768 watts. Loose connections or corroded connections cause inefficiencies. There's going to be a drop in voltage because of this added resistance, and there's going to be heat that's results as well, and that can be a problem. This shows a little bit like if you've got stiff wire and you're going to put it on it's like on a receptacle probably. You bend a little loop in it like this, and then the key is that it goes around the same way that you turn it to tighten a screw. Otherwise, you'll just spit it out or it won't be tight. Crimp-ons, if you've ever used the connectors, like there's spades and then there's rings. eyes and there's forks. You strip off a little bit of insulation and you stick the wire in there, and then you put it in a crimper and smash it down. Sometimes these are called wire nuts or Scotch locks. You've probably used these. They package them with ceiling fans and light fixtures and things like that. Screw-on connectors. You strip the wires and you put it in this thing and you tighten down the set screw, and then you just cut this off. And then I really like this. This thing fits over it and threads down on that. Heat shrink tubing, plastic that when you heat it, it contracts. It reduces its size considerably. So what they have here is they probably soldered a couple wires together and they want to insulate it. So you take a piece of shrink wrap tubing and you slip it over there, heat it up with a heat gun, and it'll shrink down on there. Soldering, iron soldering guns. If you solder two wires together, make sure you put the shrink tube on first. That's a pretty good connection electrically and in terms of construction. In terms of mechanical integrity, it won't come apart very easily because you're essentially welding metal. And this shows, if you're soldering to a terminal like this, how you bend the wire. The edge detector, we're talking about connections, and these just fit into a slot, and there's metal in the slot and there's metal on this that connect together. And the same thing inside of these. You've got pins and sockets. It's metal to metal connections. Coaxial cable shows how to do that, shows how to do fiber optics.